Chapter 17 is all about the chemical and physical properties of water. And to understand those properties, we have to understand how a water molecule is built. Okay, so this is a bead and spring model. The red bead is my oxygen. The white beads are my hydrogens that are covalently bonded to that oxygen to make that triangular structure. Okay, what that does, let me draw it here. Here's my oxygen. Here's one hydrogen covalently bonded to it. Here's another hydrogen covalently bonded to it. And remember, oxygen has 6 valent electrons. Okay, so there's one being tied up with this bond. There's one being tied up with this bond. That gives me 2 more. It gives me 2 pairs of non-bonding electrons orbiting that oxygen. And oxygen is so electronegative. If you remember back on our chapter on electronegativity, we talked about how the elements in the upper left corner, let me grab my periodic table here. Left as you're facing it. The elements in the upper left corner of the periodic table are the most electronegative. Okay, meaning they can steal electrons from other atoms easily, and they have great affinity for doing that. Fluorine is the most electronegative element on the periodic chart. Oxygen being right next to it means that oxygen is very electronegative. And what that means is oxygen is very good at stealing an electron from another atom. Okay, because it only needs 2 to fill that shell to be like neon. It's very good at grabbing those 2. So when it covalently bonds to hydrogen, even though it's a covalent bond and they're sharing those pairs of electrons, the electrons are spending more time around the oxygen than they are around the hydrogen because of the electronegativity of oxygen. Okay? Now, because of that and because of these extra bonding pairs of electrons on this side of the oxygen, a water molecule is charged. It has polarity. Okay? And polarity is just a separation. If something is polarized, you've separated it. Okay? Like the Earth has a magnetic north and a magnetic south. It has a polarity on its magnetic field, okay, because they're separated. Water molecule has a polarity of charges. So as I approach a water molecule from this side, I feel a negative charge. Okay, it's a partial negative charge. So you see that symbol, which just means partial. And when I approach the water molecule from this side, I feel a partial positive charge because the hydrogens feel like a proton, okay, which has a positive charge, because all a hydrogen atom is a proton and an electron, but that electron is being donated to this bonding pair. They're spending more time around the oxygen. So what I really feel when I approach, what I feel electrically when I approach the water molecule from this side is a positive charge and a negative charge here. That gives water a lot of its unique properties, okay? That polarity helps it dissolve things. It helps it hydrogen bond so it can stay a liquid at a vast range of temperatures. It gives water a lot of its properties. Now let's talk just a minute about hydrogen bonding. Hydrogen bonding occurs when the water molecule, the negative side of one water molecule, is attracted to the positive side of another water molecule. Okay? So I've got the hydrogen on this water molecule that has a slightly positive charge, and I've got the bonding pair of electrons on this water molecule that have a partially negative charge. These guys do here. So there's going to be a bond that forms there. Let me draw it like that. Between the partially positive side of this water molecule and the partially negative side of this water molecule. Likewise, another one can form to another water molecule. Okay, so you get another hydrogen bond forming here to these bonding pairs. Now those hydrogen bonds, those are intermolecular bonds. In other words, they're between 2 molecules. Okay? They're not the same thing as the intramolecular bond that is between this hydrogen and this oxygen. That is a covalent bond here. This is a hydrogen bond. So covalent bonding is intramolecular, it's within the molecule. That would be like the springs on my model here. Those would be covalent bonds. Much harder to break than that hydrogen bond, which is an intermolecular bond between two molecules. Okay? So when water evaporates, when it goes from the liquid to the gas state, let's say I've got two water molecules here. Here's one, here's another, and they're hydrogen bonded together. The negative side on the oxygen is attracted to the positive side of the hydrogen of this water molecule. And there's a bond that forms there, that's a hydrogen bond. Well, if you break that bond, that water molecule becomes a gas and goes up into the atmosphere. We call that evaporation. Okay? So it's a fairly weak bond. It breaks way before the covalent bond would break between this hydrogen and this oxygen inside of this molecule. Alright, so these are tightly bound together. This is a much weaker bond. So when you boil water, so I've got liquid water and it's boiling, it hits 100 degrees Celsius, and you start to get steam off of the top of your pot that you're boiling the water in. The steam is a water molecule. You've broken the hydrogen bonds at the surface of the water, and they're going up into the atmosphere, okay, into the room. You're not breaking the covalent bond. You're not making hydrogen and oxygen gas in the room. You're just making water vapor because you're breaking that hydrogen bonding. The hydrogen bonding is very important for water, for life on Earth, because what it does is it keeps water in the liquid state from 0 to 100 degrees Celsius. That's how the Celsius scale is adapted to the physical properties of water. So 0 Celsius is where water freezes and forms a lattice shape. 100 degrees Celsius is where water goes from a liquid to a gas. Okay? That's a wide range of temperatures we experience around the Earth where water can remain in the liquid state. If it were not so, life as we know it on this planet wouldn't exist. So hydrogen bonding adds to that. Okay? Also, it adds to other properties, like water has a high surface tension. And surface tension is an inward force. Those water molecules are all attracted to each other. And if you put water in an environment where it's not attracted to its external environment, okay, it's going to pull in on itself and beat up. Let me show you what I'm talking about. So I've got a piece of wax paper here, and I'm going to put a drop of water on it. Now wax is very nonpolar. Okay, it's hydrocarbons. Any way you approach those molecules, there's no charge. Okay, it's very neutral. Water is very charged because it has polarity. It has that partial positive and partial negative side. So when you take something very polar like water and you put it on something very nonpolar like wax, it beads up. Okay, see how my water is beading up and running down the wax there? It doesn't want to touch the wax, if you can look at it like that. So it makes a sphere. A sphere is the shape where it has the least amount of surface area touching the wax. That's why water beads up on a waxed car. Okay, that's that surface tension. Another way to illustrate that is if I took a penny and I started putting drops of water on it, I can get a lot of water on that penny before it spills over the sides. See how much water I've got on there? Because of that surface tension, that hydrogen bonding, where the water is attracted to itself, it's going to hold onto that penny. You can put 100 drops or more onto a penny of water before it spills over because of surface tension. Okay? That's due to that hydrogen bonding. Okay, so a lot of water's properties are due to hydrogen bonding. Some of them though, are due to the lattice formation that it forms when water goes from a liquid to a solid. Okay? When water is a liquid, it's hydrogen bonded together, but it's kind of, it's not as structured. The formation of all the water molecules are kind of spread out. Okay, so it's more dense than when it freezes. When water freezes, it takes a very rigid structure, spreads out, becomes less dense, and that's why ice floats. Okay, if I take some water, and I've got an ice cube here. So this is liquid water, and this is frozen water. And I put the ice in the water, you see it floats to the surface. Okay, because solid water is less dense than liquid water. That's unique. Okay, most substances in their solid form are more dense and would sink. But water is a little different that way. And because of that, our poles, North and South Pole, the ice there has a water underneath it. Okay, the ice floats. To illustrate that further, I've also got a beaker of isopropyl alcohol here. Now the density of liquid water is right around 1. The density of isopropyl alcohol is a lot less, around 0.8 or so. Okay, if I take ice and put it in alcohol, okay, this is just isopropyl alcohol, it sinks. See the ice sinking to the bottom there? Whereas when I put it in the water, it floated. Because the density of ice is somewhere between the density of liquid water and isopropyl alcohol. Okay? It's less dense than the liquid water, so it floats. It's more dense than the isopropyl alcohol, so it sinks. And that's a good illustration to show you how the density of water, of H2O, changes as it changes states. Okay? From liquid to frozen. Okay, now, because of the polarity of water, because it has a partial positive and a partial negative side, it's a very good solvent. And a solvent, the definition of a solvent would be a dissolving medium, a solution that dissolves other substances. Okay, that's the solvent. So water is considered to be the universal solvent because so many things will dissolve in it, especially salts. Here's why. Let me erase my hydrogen bonding here. Okay, here's my water molecule. Now, if I put salt, sodium chloride, into water, the sodium ion that was ionically bonded to the chlorine anion in that salt, the sodium ion is going to be attracted to the negative side, that partial negative side of the water molecule. The chlorine ion, anion, which has a negative charge, is going to be attracted to that partial positive side of the water molecule. So it's essentially going to tear the salt apart. So my solid sodium chloride crystal is going to dissolve when I put it in water because it's going to be attracted to different, the cation is going to be attracted to one side of the water molecule, the anion is going to be attracted to the other. Okay, and that's why water is considered to be the universal solvent. So many things will dissolve in it, especially if they're ionically bonded together. When you take something that's ionically bonded together, like a salt, different types of salts, and you dissolve them in water, you make what we call electrolytes. Okay, electrolytes are just charged ions in solution. And they're very important, especially in the body, for like, oh gosh, calcium ion, magnesium ion are involved in all sorts of things in the body. Muscle contractions, nerve impulses, things like this wouldn't occur. That's why we need water in our body, to dissolve those salts and those minerals that we take in to make them electrolytes so that they can do their function inside of our body. Okay? Now, I got another way to illustrate this. It turns out water is not that great of a conductor of electricity. And remember, electricity is a flow of electrons, okay, through a solution. So if I've just got pure water, electricity will flow through it. Electrons will be passed from water molecule to water molecule, but not as efficiently as if I add ions to it. Okay, if I put salt in water, it will conduct electricity a lot better because it's easier when you have these charged ions dissolved in that water to pass electrons from one molecule to another and conduct an electrical current. Okay, let me show you what I mean. Okay, let me hook my conductivity probe up here. Okay, this bottom graph here is conductivity. It's a measure of electrical current. And I've got a probe here